number of 3 walks in a graph. So this is basically, do they exist, or count the number of ABCD for which you can go from A to B, B to C, and C to D. But what this means that there could be, you can go A to B and B back to A, in which case A would be counted as C, right? Because there was no restriction that C and A have to be different. Okay, so this query will be very much different from a query where you actually want to count the number of paths where there's no repetition. If you really want the actual paths, then you have to do something like that. Okay? Now here you see that I'm changing the logic a little bit. So here I'm going to think of every edge relation as a function that will map to 1 if the edge exists and 0 otherwise. And if I would like to do the counting, I also need to say that A is different from B, from C and D, all A, B, C, D are all different. So there will be a lot more complicated stuff going on here with this indicator functions. But if you sum up over all possible A, B, C, D, that should give you the number of 3 walks, or 3 paths in the graph. And this is a more complex query than the one before. I'm not going to show you the REL code of this. It looks exactly the same as the logic. Okay. And later on, when Val and Dan talked about an algebraic language with the semi-ring, then you will see stuff like this occurring very naturally. So this is not logic anymore, right? This is something that you can do algebra with. So I'm trying to, in this introduction, to connect all of the talks that you will see in this bootcamp together, and you will these will start to show up. Another problem is, say, all pairs shortest path, right? So in English, you want to say that, well, compute the shortest path length between every pair of vertices. So here you will need kind of another query language in order to express this problem, right? And the one that Val and Dan will talk about is something called data logo, where you will express the problem much like in math in this way. So you will say that, well, the query says, compute for me the shortest path between x and y. That's going to be the minimum between the length of the edge from x to y, or a minimum over all possible z for which the length from x to z is this much, and then you add the length from z to y. Okay? So, but for this query, there are actually at least two different ways to express it, right? You can also, start with the same base case, but then in the recursion, you could recurse it on two, qx to z and qz to y. So mathematically, there are 2 ways to express this problem. And it turns out that if REL, a system, sees this query, it's actually not completely trivial if you express it in a way that is not very easy to optimize. You could express, the all-pair shortest path problem this way. This would be the first way. This is called linear recursion, where I hope you can see this from the back. Where it's exactly like the math formulation, all pair shortest path, but this Q occurs only once in the query. Sometimes you could express it so that it occurs twice, and it's actually harder to optimize in some ways than the first one. And then you could actually query this graph. So this is the same graph, right? Typically, people really are not interested in all possible, shortest path length between all pairs of vertices in a graph. You have 9 million vertices. That would be 9 million by 9 million, or whatever, 2 million, right? Who has the time to examine, 4 trillion pairs of vertices? Usually they're interested in something very specific about this query. So you could ask a query, well, what is so let's say I want to query this, from vertex number 2, what is the shortest path length to all of the rest of the graph? Okay? So this would be the single source shortest path problem. And And then in the output, you may want to ask, well, what is the maximum distance from this number 2 to the rest of the graph? Okay, so this 2. And then if I run this, it should give me something sort of like the diameter of the graph, but center at this vertex 2. And if you range this over all vertices, you get the actual diameter. Okay? So in this case, it returns 7 or so. So the graph has a pretty small diameter. But you can see that the query returns very quickly. And that's thanks to demand transformation, which is another topic that Annie Liu, who's here earlier, who might give you a talk on. The idea is that you can compute something like this without actually computing all possible pairs, 9 trillion, whatever, output size. Okay? So that's another query optimization problem. Okay, so with these examples, you probably are somewhat convinced that there are all these queries that all of you have been looking at, and if they are baked into a relational database system, then the optimizer, the query optimizer, has to process those queries and return the answer, come up with a query plan as quickly as possible. So that's a very brief introduction to the query optimization and evaluation problem. Yeah. Okay, so the main problem looks something like this. So we have a query. And then we have a database that stores, like the edge relation of a graph. And we also have some statistics on the data that are in the database. I'm going to call this SD, the statistical profile of the data in the database. And then we would like to return the answer to the query. Okay, so the problem is, given Q and D, compute QD is in the most efficient, and dare I say, optimal way possible. So optimality is a very, very strong word. I don't want to claim that, but let's see how far we can push this notion. And if we have, let's say, some kind of update to the database. So you remove an edge from the graph, you add a new edge to the graph. Given the same query, is it possible to compute the output of the query without recomputing the whole thing? So in database, Dan on Friday is going to talk about incremental view maintenance. And I guess in algorithms, this is called dynamic algorithms. And we do have a workshop with a few talks later in September on dynamic algorithms. Okay? So that's IBM problem. I think it's basically the same problem. Yeah? Okay, so to make this formulation a little more precise, then I have to tell you what I mean by a query. And in this talk and the next two, we'll be focusing mostly on form conjunctive queries and a little generalization called a sum product query. And sum product query is a concept that we borrowed from AI. And in one of the tutorials, Guy and Yu Jung will talk more about AI and query evaluation on circuits that has a lot to do with sum product type of computation. There are other types of queries, say first order, second order, of which I don't know if you can ask Fokyeon to give a talk on complexity of different types of query classes. I'm trying to get topics lined up for the rest of the semester. Then that will be it. We have Nikos who can give you rank enumeration talks, different types of queries, many different types of queries. They are very practical, extremely useful. What is in the statistical profile? So in my talk, I'll be just talking about one particular one, called the degree constraints. It's sufficiently simple, but also quite powerful enough to build a database on. But there are many other constraints, frequency moment constraints, histogram, samples. You can sample from the database. And Marcelo, on Friday, he will give a talk on sampling in the database. You could build machine learning model about the data, and then you learn something, and use that information to optimize queries. Okay? What do I mean by optimality? Well, so for this talk and Mahmoud's talk, we'll be talking about worst-case optimality and instance optimality. But in general, we'll need the fine-grained complexity folks to tell us more about various ways to, how do you prove that the answer to this query is optimal in some way. You have to make some complexity theoretic assumption. So Virginia, Nicole, and Yin Zhang on Wednesday and Thursday will give you some flavor of that. And most importantly, I'm not sure if you realize this, is that in the picture that I showed you earlier, the query optimizer does not optimize. You have to kind of code up the optimizer before you see the query. So there are two ways to do this, right? You might want to say, well, if the query is a triangle, I'm going to run this algorithm. If the query is a 4-cycle, I'm going to run this algorithm. But the number of queries is infinite. When you code up the optimizer, you cannot have an if then else, like that, right? The optimizer has to be, in some sense, universal, and it will have to work for every query. So the optimizer has to be done before we see the query, and this is a very subtle and important point. And in some ways, it's basically a meta algorithm. Given a description of the problem, is supposed to output an algorithm to solve the query. And so in my 3 tutorials, I'm going to be talking about basically 3 basic meta algorithms. So the first one is join. It's actually a meta algorithm. The second one borrowed heavily from the AI community, from machine learning, is the variable elimination technique, which is a very highly generic way of solving a query. And then tensor decomposition. So those are very general techniques that can be applied to a bunch of different problems, including all of the problems that you have seen just now. Okay, so that's basically the outline of the rest of the talks and the tutorial. Okay, any questions so far? All right, so let's go to the first problem. This will be on cardinality bounds and worst-case optimal join. So this is a little bit of a detour in some sense, but you will see eventually how this is actually tightly connected to query evaluation. Okay? So this is our problem. We have a database, and we have a profile, some kind of samplings or some kind of statistics about the data in the database, like the degree of vertices in the graph or the number of edges in the graph and so on. And let's say we would like to know the following. Let's forget about answering the query to begin with. Let's just say that I would like to estimate an upper bound on the output size of this query. So if we were to list all of the triangles in the graph, then this will be saying that, well, if I know the number of edges of the graph, can I get an estimate of the maximum number of triangles that we can get out of this query? Okay? So this is a much simpler query than that query, but let's see if we can get this maximum estimation. This is, in databases, this is extremely useful because, for example, if you knew this, you could use it to, let's say, cap the memory amount that you will use in answering the query, for example. This can be used for cardinality estimation, which is a very important component in the query optimizer. Okay? So I will kind of try to simplify the question, and then later on, we will go back to answering the actual query. Now, so there's one notion of optimality, which will come back to in the second lecture, second tutorial, which is worst-case optimality. And worst-case optimality basically says that the following. So suppose that we somehow knew how to answer this question. Then a join algorithm is an algorithm that can answer this query in time that the input size, that's the input database, right, plus the worst-case output size. Yeah? So this is not quite instance optimal in the sense that this is not QD, but it is the worst-case output among all of the possible databases for which it has exactly the same statistics as this profile. So the idea is that we are not going to process the query over the database. We are only looking at the statistics. Let's say the number of edges of the graph or something, or number of vertices of the graph, and get the query to run in time that is the worst case possible. So there's actually some input for which this algorithm is instance optimal, right? The worst case. It's a pretty weak notion of optimality, but let's see if we can actually get here first.
So when you say that's cardinality of QD? So it's like the number of things that satisfy the query?
That's right, precisely. Yeah. It's the number of tuples in the output. Okay, so let's say the query was listing all the triangles in the graph, then this will be the number of triangles. The runtime would be number of triangles, and that will be like m to the 1.5, for example, and the runtime would be O of m to the 1.5. Okay.
Yeah. What's that notation, like vertical equals the subscript?
Oh, yes. Sorry. Thanks for the question. The question was, what is this notation? This notation means this is a maximum over all possible databases D prime, which has the same statistics as this D. Yeah. So like all possible graphs that has exactly the same number of edges, let's say, so this means satisfies or model is the logic notation. Go ahead, Remy.
It doesn't say more enables that many number of objects. So it can be small.
Yeah, so it depends on what we mean by this profile. So I will come to that. Yeah.
So when you do not have any statistical profile available, then what will happen to the second term? So
yeah, so if SD is empty, then D prime will be arbitrary. So it's over all possible data.
So it is then not in time, just in D. It is then the time is unbounded. So
that's right. Yeah. So if we don't have any information about the database, then the maximum output size is basically infinite. But we will, in most cases, we'll have to assume that we know something about the data. Okay, so for the query, so for now, let's just focus on 4 conjunctive queries. What does that mean? It means that it is a query in which all of the variables appear in the output. So in a graph database, that would be like this. You have the body, and then in the head of the query, you want all possible triangles, for example. Or in a movie database, you would like all the variables, like director, actor, movies, and so on. So there's no exists something. What that means is it will project away some of the variables, right? So for now, let's just focus on queries for which every variable is in the head of the query. And then we'll remove this assumption in the coming tutorials. Okay, so more generally, the model is like this. So we are given a hypergraph in which for every hyperedge, there is an atom, or there's a relation for that hyperedge. And we would like to answer the following query. List all of the tuples that satisfies every single atom in the body. So the simplest example is the hypergraph. In this case, it's just a triangle. And then we would like all tuples ABC, for which AB is in E, AC is in E, and BC is in E. But in general, this hypergraph could be, like in the previous example, it could be this hypergraph has an edge, director, actor, movie, actor, age, and so on. Technically, this may not be considered a conjunctive query, but for the purpose of this talk, think of this as a conjunctive query because of this disjunction here. But for the purpose of this talk, you can think of this as a relation. This is a relation on the variable actor age, but it has to be either more than 20 or different from 10. You could have regular expression matching relation too, and that's fine for the purpose of this talk. Okay, so hopefully this model is okay with you. We'll have maybe a few more examples, but it's important to get the model in mind that we are given a hypergraph which captures the structure of the query. Every hyperedge, there's a corresponding relation. And then the query is, list for me all of the output tuples that satisfy the relation that are captured by the hyper edges in this graph. Okay, so that defines the query, and the next topic is what is in this statistical profile, and we are going to focus on just one notion. It's called the degree constraints. And what is a degree constraint? So imagine we have a relation like this. This is a ternary relation that has 3 variables: actor, movie, and role, right? And let's imagine we have a vector on the actor variable in which we are going to count for every actor how many rows of the table the actor occurs in. So here we have, Alice occurs in 1, Bob in 4, and Carol in 2. Yeah? This is a humongous relation still because the number of actors is maybe in the millions or so. So this will not be in our statistical profile. Our profile is going to be some kind of summary of this vector. It will be a norm. And in this case, I'm going to just use the infinity norm of this vector. So this infinity norm of this vector is going to be 4, right? Because so Bob occurs in 4 movies, and that's the maximum. So this constraint is called a degree constraint. It says that every actor occurs in at most 4 rows in this table. Okay. Now, in general, instead of this actor, we are going to have, you could have, for example, a vector on actor and movie together. Okay. So in this case, for every combination of actor and movie, how many rows of this table does this actor and movie belong? Okay. So this is a different degree constraint. And assume that if this infinity norm is 1, then in database, this is called a functional dependency. This says that for every actor and movie, I know that there's only 1 row, assuming, then this is a functional dependency. You could also have a group by of nothing. So this says that, given nothing, the infinity norm of the count, in this case, it'll be 7 because we are counting everything. We are not grouping by actor or actor movie or anything. So in this case, this is called the cardinality constraint. It's the size of the table. Okay. So this abstraction, even though very, very simple, is actually quite powerful because you can use it to capture a lot of very common statistics that you would have in a database. So if this was the edge relation of a graph, then you might want to say, well, D of U is, you have UV as vertices, right? So D of U infinity, that will be the maximum degree in a graph. Right? Or if you have D empty set infinity, then that will be the number of edges in the graph. So go ahead, Remy.
Should all of these be bold-faced? The accurate. Up here.
Up here.
Should these also be bold-faced?
Oh, yes, I think so. So I usually use boldface to denote a vector, and then a component of the vector is not bolded.
Right,
But it's
you're looking at the Alice outlook of the actor.
Oh, you mean here?
Yeah. So here the actor is still the vector, and then we're just looking at the Alice.
That's right. Yeah. So this is just a component of this vector. Okay. So in general, a degree constraint is a triple x, y, and n in a relation R, and what this says is that for every x, the number of different y's is bounded by n. So this is a general degree constraint. For every x, the number of different y's is bounded upper bounded by n. And these will be our central subject of the statistical profile that we have in the database. Yeah.
Do you get a need for constraints across 2 relations? What would you do with the inclusion dependency? Do you have this in the optimizer?
Yeah, so Fokion's question is, in general, how do we deal with constraints that do not, that correlate, but they span across tables? My general answer is that we don't know. In general, it's pretty hard to deal with those constraints. Now, typically optimizers deal with those by doing sampling, because beforehand you might have a query in which you ask for the make to be Honda and the manufacturer to be Honda and the make to be Civic or something, and if they belong to different table and you're asking this query beforehand, it's extremely hard to know beforehand that these two sound strongly correlated, right? So you basically have to kind of sample into the database to know for sure that the output is only one. For every Honda, or for every Civic, there's only one Honda. We don't have that kind of model to model those situations yet. I think that's a great open question, actually. There are much more powerful constraints that we need to be able to capture in a database, but this formalism just doesn't make it yet. Okay, so now we know the constraints, right? And let's go back to our question: what is the maximum cardinality of the output satisfying these constraints? And in order to describe one approach to answer this question, we'll look at a hierarchy of set functions. So I'm going to look into a collection of set functions on, actually this was supposed to be V, the set of variables in a query. And we'll look at the ones for which are non-negative and monotone. So h of the empty set is 0, and then if x is a subset of y, then h of x is a subset of h of y. And then as we are adding more and more constraints to these sets, we are narrowing down this collection of set functions. So for example, you can have sub-additive functions which satisfy this inequality. The one that is most important to us is submodular function. So is both non-negative, monotone, and submodular, which means it satisfies this inequality. And there's a class of functions called entropic functions, which are basically entropies of some discrete distributions. And then as we are moving down, at the very end, at the bottom of this hierarchy is a set of modular function, which is very, very simple. H of x is the sum of h of the elements in x. And these have to be non-negative. And so the thing that I would focus on in a little bit is the polymatroids, or submodular functions that are monotone and non-negative. Okay? And you will see how they show up in proving a bound for this query just in a moment. Okay, so remember that we are interested in this quantity. What is the maximum output size of a query over all databases satisfying a given collection of degree constraints? So SD is what we know, and we want to maximize over all of the D prime that satisfies the same degree constraints. Okay? And for convenience, we will actually upper bound the log of this quantity. You will see why in a moment. Now, there's something called the combinatorial bound, which will be an exact equality. It's probably computable, but impractical. And now I'll explain why. And then because of that, we will have a hierarchy of bounds that will kind of approximate this as much as possible. And the one that we'll be focusing on is polymatroid bound. And I'll have an example to explain where all these bounds come from. Actually, only these two bounds. We'll ignore the rest of the bounds. Okay. So let's look at one example for now. Go ahead, Paris.
You say it was probably computable, or what do you mean exactly by that?
Yeah, I'll give you an example, and you'll see. Yeah. So
It depends entirely on what S is.
that's right. Yeah, exactly. Yeah.
It's like you just run all databases and then find the size.
Yeah. For some S, we actually don't know how to compute, but for simple S's, then it's computable. For one example. Did you have a question?
Yes, I was wondering what was sigma.
Yeah, so I'm not going to have time to explain these. This is just a variable ordering of the query that is a parameter to this bound. Okay, so let's look at an extremely simple example, the triangle query, famous triangle query. And many of us work on click queries and triangles, and this will hopefully resonate with you. So in this case, the database consists of three relations, R, S, and T, right? RAB, SBC, and TAC, or CA, doesn't matter. And our statistical profile has the cardinalities of these three relations, so R, S, and T. So it's just like the edge relation of a graph. And you know the number of edges, but nothing else. Okay? Now, here is where in a database setup, this is a constraint satisfaction problem, right? Because you want to know number of triples that satisfy all three constraints. But in a database, the difference is that typically the number of constraints is small. In a query, you don't have a lot of constraints, right? You have, I don't know, up to 10, 50 relations or so. But every constraint is very, very large. Like, the edge relation of a graph could be like billions of tuples in it. So please have this model in mind that it's very vertical, right, instead of horizontal. As in a constraint satisfaction problem, it's quite horizontal because the number of constraints is very, very high. Okay, so now the question is, how do we bound the output size of this query? So here's the combinatorial bound that we can set up. So let's say that we have an indicator variable for the fact that AB is in R, AC is in S, and BC is in T. Now, obviously, this is a triangle if all three indicator variables are 1, right? And so if you sum over that, then you will get the number of triangles. And the cardinality constraints will be, well, the sum over all of the indicators for R is less than R, for S is less than S, and for T is less than T. So those are the main constraints. We have billions of indicator variables. This is kind of a horrible integer programming problem. You can turn this into a linear integer program, but it doesn't help because the number of variables is just too big. So this is what I meant by computable but impractical. But this is only for this kind of very, very simple constraint. So as Brian pointed out, if you change this to general degree constraint, it's not obvious how you set it up even.
But even here, like how do you define the variables in this problem, right? So, for example, where does A and B range over?
Right. Yeah, precisely. So even here, computability is kind of questionable. I guess you could do this here because you know that the domain, the active domain of these relations are bounded by R and S and T. So by an isomorphism argument, you can assume that A ranges from 1 to the size of R and so on. So you can make some kind of assumption to set it up. But in general, it seems to be pretty hard to do. Okay, so that's the combinatorial bound. Now, so the next bound is based on the entropy argument that this came from probably even earlier by a famous paper, Fanchong, Lundgren, Frankel, and Scherer. And it goes like this. So let's actually fix a worst case input for this query, so R, S, and T. And for this worst case input, we will get a table of triples on Q, right? It's probably a pretty big table, but it's going to be finite. So let's select a tuple, A, B, and C in Q uniformly at random. So this is for the worst case input. Right? So it could be a Q could have trillions of tuples. Let's just select one tuple out uniformly at random. So what do we know about this distribution? Well, we know that because it's uniform, the entropy of that distribution is going to be log of the support, right? And the support, because it's worst case input, is exactly the quantity we're interested in, right? So that's the quantity, and log of the support is H of ABC. And the marginal entropies will be less than log of the support of the projections of this distribution onto S and onto T. Because the uniform distribution has the maximum entropy. And so this will be less than the 3 logs, right? And finally, the most important constraint is that H as a function, it has to be entropic. So the notation for entropic function is gamma star 3. This has become kind of standard in information theory, so do not ask me why, I use this notation. Okay, so it's entropic function. This is a function over, think of it as a vector that has 7 dimensions. There's HAB, HABC, HBC, HABC, HABC, and so on. For every subset of 3 variables, there's an entropy value. So H is actually a vector, dimension 7. Right? And it has to be entropic. And how do you characterize this region? That's a humongous problem in information theory. But at least we can set it up, this optimization problem. It doesn't seem to help because, we have just turned a problem that seems to be very hard into another problem that also seems to be pretty hard. But is everything okay so far? So this is just an upper bound on the quantity. It'll be easier from here on computationally anyways. Okay, so the next quantity, what do I say? So this was an equality, right? So this is not an upper bound or anything yet. This is for one particular entropic function. So we know that there exists an entropic function for which we have an equality. Right? So in order to have an upper bound, all we do is to optimize this over all possible entropic functions. That'll be our upper bound. Right? So this will become less than equal to the max over all its possible entropic functions. Okay? So this is the entropic bound. That's the first bound in our hierarchy. We're going to go down this hierarchy. And the next relaxation is that, because characterizing entropic functions seems to be pretty hard. So what we do is we relax it a little further. Instead of taking entropic function, we'll take polymatroids, which is just one layer up. So here we have, monotone, non-negative, and submodular function. And the beauty of this is that the polymatroids they have linear constraints. So now we can solve them now, right? Because remember, monotonicity is just, h of x less than h of y is a linear constraint. Submodularity, all of them are linear. Except that the dimensionality of this vector is exponential, right? Because for every subset of the set of variables, we have one component of this vector. It's exponential, however, it's exponential in the query size. And as I said earlier, in databases, the query is pretty narrow. The data is big, but the query has like 3 variables, 50 variables, whatever. Exponential in 50 is impossible, but still, in principle, is a lot smaller than the billion variables that we have. Okay, so this is our polymatroid bound for the triangle queries. And yeah, so the main lesson so far is that this bound is a linear program. So it's really, in principle, you can compute it.
Okay. Is this the same thing that you call
No, so this is beyond almost entropic. Yeah, I didn't say anything about the almost entropic yet. But the reason is that, in general, in higher dimension, the region of entropic functions is not even closed. So you actually have to take the topological closure of that, and it'll become the set of almost entropic function. But we are not doing any optimization over that. We even relax it even further into the set of polymatroids, so that we have actually a handle on how to solve this optimization problem.
Just go back to your hierarchy of set function.
Sure.
Where are we?
Yes, so we're right here. We are at the polymatroid Yeah, because we actually set up an optimization problem over this set, but this set seems to be very hard to characterize. Even after you take the topological closure, it's still hard to characterize. So we move it up one more level. Okay, so from the entropy argument, we got the polymetroid bound, which is great. So now let's actually connect this to a few more bounds that we know. So there's this very cute idea from Lovas from a long time ago, I think like 1982 or something. It goes like this. So here we have this optimization problem, maximizing h of ABC subject to these three constraints. And h is in gamma 3, which is a set of entropic functions, polymetroids over three variables. This is our problem so far. That's the polymetroid bound. Lovas came up with the following idea. So suppose that we define a modular function. Remember that a modular function is a function where g of x is the sum over g of the elements in x. It's a very, very simple characterization, and it goes like this. So let's define g of a to be h of a, g of b to be h of b given a. So this is much like conditional entropy, which means I should probably write something. So h of b given a is equal to h of ab minus h. So that's exactly how conditional entropy is defined. And similarly, g of c is h of abc minus h of ab. It's a conditional entropy of C given AB. Yeah. So we have now three numbers, GA, GB, and GC. We have three numbers. So now you can verify that for these three numbers, GAB, because it's modular, so it's GA plus GB. So this is H of AB by definition. And then GBC is GB plus GC. And by submodularity of H, this will be smaller than H of BC by definition. And then G of AC is smaller than H of AC by submodularity of H. And so what this means is that G is a modular function that satisfies all three of the constraints that H was supposed to satisfy, because they are even lower, right? G of AB is smaller than HAB, GBC is smaller than HBC, and so on. And modular functions are polymetroids. They are a special class of polymetroids. So we have found a smaller class of functions within the class of polymetroids for which G of ABC is H of ABC, because you can telescope the sum from here to here, right? So it has exactly the same objective, it satisfies the same constraints, but it is smaller. So that's great. That means that we can now just solve the problem over the class of modular functions instead of polymetroid. And because we can solve this over the modular function, the linear program now has only poly size, because there's only one variable for every variable of the original problem. This is a lot easier constraint to problem to solve. Okay? So that's the modular bound. Okay, and so if you write that down, this is nothing but a vertex packing linear program. Right? It's a vertex packing linear program. If you take the dual of that, you will get a fractional edge cover linear program, and that was basically what Albert and Groy and Marx in 2008 in a Fox paper. Has a lot of influence in the story I'm telling here. So if you take the dual of this linear program, then you get the fractional edge cover linear program to bound the same thing. Okay? So this is basically you have a coefficient for every edge of the graph, and then for every vertex, the sum of the coefficients have to be greater than 1, and then the bound will be going to be this. And if you take the exponential of this, it will be like r to the lambda r, s to the lambda s, and t to the lambda t. Okay? So that's the fractional Edge-Cover bound that bounds the number of triangles in a curve. Okay, so you could go a little further and you say that, well, you can also take the integral Edge-Cover bound. And it's kind of a silly thing to do because you will get an even a bigger bound, right? Because if you remove the constraint, then the mean will, the mean should increase. Yeah, the mean will increase. So, but it will be somewhat interesting to point out later on that this integral Edge-Cover bound has kind of a database interpretation. So that's all I wanted to point out. Okay, so what we have seen so far? We have seen so far that for the triangle example, this is only for the triangle query, the quantity we're interested in can be bounded by the entropic bound, which turns out to be equal to the other three bounds. Okay, so the next question is how tight are the bounds? So because I'm running.
Sorry, you just said it's equal just for this example, but you haven't shown us why, or I mean, you said that the entropic bound was hard to compute, but for this particular example, it's possible. Is this what you mean?
I see. So you are, yeah, so I haven't shown that the entropic bound is actually equal to this bound yet. That's
Okay,
the question, right? Yeah.
And it's very specific to this example.
That's right, yeah. So it turns out that you can prove that for gamma 3, the polymatroids and the entropic region are actually the same region. It's just so happened that for this example that in general, this will have to be an inequality. Okay, so because we are kind of running a little short on time, I'm not going to show the lower bound argument, but I want to at least get to the end story that I would like to convey, is that that exact same argument that we have seen so far is going to work for general degree constraints. Okay? Remember, degree constraints is basically the collection of triples x, y, and n, which says that for every x, there are at most n y's. So that's the collection of degree constraint, right? And the exact same argument is going to imply that the quantity we're interested in is bounded by the entropic bound. Okay? What does that mean? Well, it precisely means the following. So given the degree constraints, and from the degree constraints, we are going to turn them into a linear constraint on the on this polymatroid or entropic function h. So h of y given x is less than or equal to log n. You see that it's very easy to turn one into the other. Right? One is combinatorial and one is information theoretic. And once we have this bound, then you can, the bound that we are interested in is going to be an optimization problem over, this is the almost entropic region, and this is the, these constraints right here. Okay? And we are taking the soup over h of v. So this quantity is called the entropic bound. And if we relax this to only polymatroids, then we get the polymatroid bound. And this bound is computable. It's just a linear program, so it's great. And one simple example, going back to the triangle query, if you are going to take the polymatroid bound, then you will get, for example, the number of triangles is less than n to the 1.5. Sometimes this is known as a Loomis-Whitney inequality. Okay, just plug it into the bound and solve the linear program, you'll get n to the 1.5.
And I think it's worth pointing out that if you just set the variables in your LP written back there to 1/2, you would recover the same thing.
Precisely, yeah, thanks. You're right.
Yeah, it's a bunch of variables, and their pairs have to, the sum of the pairs have to be at least one. So you sum all the half, and you'll get the same thing.
So we don't really have to solve the optimization problem. We just plug in a feasible solution, and we get it.
In the previous slide, what is the assumption on the query? Every full conjunctive query? Or?
Oh, yes. This query has to be a full conjunctive query. Yes. So, yeah, for this talk, all queries are full conjunctive. And then later talk will relax that assumption. Okay, so this is kind of a trivial example, but there are other examples that are not that trivial. Let's see. Oh, okay. So suppose you also have a triangle query, but in a database, typically you will know that some variables are key variables, like primary key in a relation, right? So for example, if you knew that B implies C, so B is a key. So that means that there's a functional dependency from B to C. Now, in this case, the extra constraint that we have is that the conditional entropy of C given B is 0. Right? So we have one extra constraint, and you plug in the bound. It's, constraints are just like before with this one extra one, but now the bound drops significantly. So instead of n to the 1.5, now we just get n.
So this is correspond to the out degree of B is 1, and it has just an edge from B.
That's right. Yeah, precisely. And of course, this works even if the out degree is 3 or 5. We just plug in the log 3 or log 5 here, and just by solving a linear program. But this time, I guess you have to solve the linear program. It's not obvious to plug in the 1.5, 1/2 anymore. Yeah, this is one of my favorite examples. It's extremely simple. In database, sometimes you write queries like this. What is RA and SB and A plus B is equal to 5. And like the simplest example that illustrates the strength of this bound. So here you will know that, given A, then you have B, given B, then you have A. And this degree constraint comes from this little relation, A plus B is equal to 5. And if you plug in this, a conditional entropy, then you will get the bound to be the minimum of R and S. So as a human reasoner, you would be able to infer this, right? Just say that, well, you have a conjunction of R and S, and then there's an FD going A to B and B to A. And obviously, the size of the output is a minimum of the two quantities. But the entropy argument gives you that kind of automatically, just as good as we would reason. Okay, so that sets up the bounds, and there are other examples. So now let's go to the research questions. I have about 3 minutes left, and there are infinitely many research questions, and here are some of them. So the first thing is, it's actually open whether or not the entropic bound is computable. We think it's not computable, but we don't know. And Dan can give you, an overview of where we are with these entropic bounds. The second question is, this is extremely annoying. We worked on this for some time. Is the polymetroid bound even in P time? So at the surface of it, the polymetroid bound is, a linear program over an exponential number of variables and constraints. So it should not even be in P. But we also have seen examples, such as a triangle example. You go from polymetroid to modular, and it suddenly is in P. So, is it the same in the general case or not? We don't know. And if it is not in P, we have some good reason to conjecture that it's not in P, then what are the classes of inputs for which it's in P? Because it's very important in database to be able to do cardinality estimation within P time. And then...
By inputs here, you mean constraints?
I meant the constraints, yes. The structure of the constraint somehow. And then when is which bound asymptotically tight? So we know that if the input has only cardinality constraint, then it's basically tight, but it's not exactly tight. I think Albert in the AGM paper showed that even approximating the upper bound is like hard, assuming ZPP hardness or something like that. So yeah, it's not a completely trivial thing to even set this up properly. Yeah, and then approximate the bounds efficiently. What about beyond conjunctive queries? If queries have disjunction in them, what do we do? If it has other complicated structures. And then, degree constraints is just really one set of constraints. can we deal with more interesting constraints? So Mahmoud can give you a talk on adding conditional independence constraints. So that gives the structure of the query quite different flavor. Frequency moment constraints, histogram constraints. In database, it's very common to have histogram. So you will say that, well, for this range of vertices in the graph, the maximum degree is 5. For a different range of vertices in the graph, the maximum degree is 7, and so on. So you divide the graph into different communities, and then you have different bounds for different community in the graph. And yeah, most of these are really open. So yep, I have a lot of slides, but I think that should be it for the first tutorial, where the bound was set up and a lot of open questions. So in the later ones, I'm going to try to make use of the polymatroid bound to do something interesting with them. So thanks for listening.
We still have time for some questions. Yes, please, Pierre.
Can you go back to the inequalities between the bonds? You had one slide where you had all the different bonds with inequalities. Can you just go back to that?
Let me actually give you a more complete picture. It's about the same, right?
Yeah, sure. So my question is, do you have examples for all of them where the inequality is strict? Or are there still, so for all of them you have examples?
Yeah, we have examples for every one of them to be strict, and kind of the gap is unbounded for some classes of points.
It is that we beyond conjunctive queries, is it also interesting to be beyond full?
Yes, it's definitely interesting to go beyond full conjunctive queries. So some of the frameworks that we discussed here can be used for non-full conjunctive queries. The only difference is that instead of maximizing over h of all variables, you just maximize it over h of the subset of variables in the head of the query, and everything goes.
Okay, then let's thank Hank.